Hello, welcome back. Today we will discuss Poisson-Cohn reaction, mainly the Poisson-Cohn regiochemistry. In the last class we have introduced the Poisson-Cohn reaction. It is an oxidative cyclization reaction between alkene, alkyne and carbon monoxide. We get cyclopentanone as a product. That is a very interesting fact. Now, how to put together all these three components to give only one product is really an interesting task. We have seen that mechanism also in the last class. Today, we will discuss more about the regiochemistry of this reaction and also the real examples how it was a stoichiometric reaction first and then an intramolecular version of it, and subsequently it has become catalytic as well as intermolecular reactions are nowadays possible. This has been utilized quite a lot for natural product synthesis. Even asymmetric versions of the Poisson-Cohn reaction is possible. So, all these will be discussed today. Let us look at the key factor that determines the regiochemistry in the Poisson-Cohn reaction. Okay. So, Poisson-Cohn regiochemistry. Now, as we were mentioning, the substrate we have in hand is olefin, okay, and an alkyne. Usually terminal alkyne works better, but if it is an internal or disubstituted alkyne, still it works. Let us say you have RS small group and RL large group. One large group on the alkyne, another small group on the alkyne, and if they are same, you do not have any problem. If you have olefin, let us say substituted as R, the product or rather products in this case one can have is two different one, okay, where RL could be there. RL usually at close to the big L or R group will be close to the carbonyl and the small r will be far from the carbonyl. Now, in one orientation you can have R at this position close to S, another orientation you can have or another regiochemistry you can have where R is close to the carbonyl, right. Always RL is close to the carbonyl. Okay. So, as you can see RL and RS, one is large, one is small. The large one is always close to the carbonyl, large substituent is close to the carbonyl, the small substituent is far from it. Now, in this cyclopentanone, the R which is coming from this olefin, this R, now this R can be far from carbonyl or close to carbonyl. These gives rise to the two regioisomers. Now, as we are saying, RL or the large substituent will be always close to carbonyl. And if these RL and RS is not or are not H or if these are not hydrogen, then mostly we get this compound 2. Okay. So, the first fact is you will have RL always alpha to carbonyl, RL will be alpha to carbonyl. That is the first fact. Second fact would be if RB is not equal RS is not equal H, then we get 2 as the product, the second product we always get. If regiochemistry at alkene actually, so the R whether it is at the far position or close to the carbonyl, it will depend on the alkene as well as alkyne. So, the type of alkene and type of alkyne will determine whether R is at this position or R is at that position, right. Also, this can be controlled by ligation on the different metal center that we will be discussing in a moment. So, what we have seen so far is the rules that governs to give the regioisomers two isomers are possible. As you can see, the substituent R on the olefin can be close to carbonyl or far from carbonyl. Now, that will be determined by the olefin itself and in combination with alkyne substituent. Also, we know that the ligand on the metal center required for this reaction can influence the regiochemistry of the product formation. Another important thing is, if your those alkyne substituents are not H, then usually we can get the product where R from the olefin is alpha to the carbonyl moiety. So, these are the things we will see again and again. As I was alluding to, there was first the stoichiometric version for long, and then subsequently in mid 90s we have seen the catalytic version of this reaction. Not only intramolecular reaction, even intermolecular catalytic version was also put forward later on. Let us look at some of the Poisson-Khond reaction examples, and we will be discussing 2-3 examples in terms of the natural product or complicated molecule synthesis first, then we will be moving to the catalytic version of these reactions. Okay, Poisson-Khond examples. Let us look at a substrate where you have OTBD MSO and an alkyne together with an olefin. Okay. You have this olefin and alkyne together. You would like to do the Poisson-Khond reaction in presence of CO. Under the standard reaction condition of the Poisson-Khond, what you will get, it is a stoichiometric reaction. At the beginning, as I said, this is the product you get, cyclopentenone with this very good yield, something like nearly 80% yield can be obtained, and this is the product that is the major product, 26:1 regioselectivity, or the regiochemistry can be maintained quite very effectively. Now, this is reported in tetrahedron in 1985 by Magnus. Okay. This is an intramolecular reaction. As you can see, the bond formation between this alkyne and olefin, and then there is a carbonyl that is coming into picture. Okay. So, overall you see the Poisson-Khond reaction occurs quite efficiently, nearly 80% yield, and 26:1 for the major product formation. Let us look at another example where similarly an alkyne and olefin will be put together along with carbon monoxide, CO2, CO8, and stoichiometric amount of them, and then this reaction will be giving you to the desired product. Another example, NTS, of course alkyne should be straight, but just to give you the real feeling how it might will be happening, we have drawn like that. Now, this is once again you have an alkyne, you have an olefin together, and you are doing this reaction in presence of dicobalto octacarbonyl and then with dichloroethane. Overall, in this reaction, what you get, this is again by Magnus in tetrahedron letter 2002, you get the product, desired product, and that is the cyclide. It is a fused cyclic part compound that one get. So, the 5 membered cyclopentenone, and then your desired product that is there in very good yield, depending on this nearly 60 to 70% yield can be obtained. Now, these are the really powerful reaction for constructing the cyclopentenone kind of intermediate. Now, we will see another example where once again an alkyne and olefin along with the carbon monoxide will put together in presence of dicobalto octacarbonyl species for giving you the cyclopentanone intermediate, right. Let us look at one more example of this series to establish the fact that these oxidative cyclization are a reliable technique for synthesizing these cyclopentanone products. Okay, now, the example we have had in hand is the one where it is substituted very efficiently. Once again, an olefin, terminal olefin and an internal alkyne are participating. This is a report by Jared in 2002. So, this is by Jared, Angwante 2002. 411783. The product in this case, the starting material you need is again the dicobalto octacarbonyl species, and overall you get this product very efficiently, and the desired cyclopentanone is formed rather easily in these cases, right. So, from there on plus minus 13 deoxyceratine can be synthesized. Those are the natural product synthesis can be done very effectively under these conditions. So, what once again you have seen here is a terminal olefin and an internal alkyne put together in presence of carbon monoxide to give you the desired product, which is going to be your cyclopentanone, which can then be further taken towards the natural product synthesis. These are indeed very powerful technique, and whenever you see a 5-membered ring with cyclopentanone motif or any further functionalized motif, this is the way perhaps to synthesize it reliably, and the yields are usually quite very good. Okay. Now, let us look at the catalytic version of this reaction, where in mid 90s it was first reported, and we will see first reaction of course was intramolecular catalytic version, and then subsequently people put forward even the intermolecular catalytic version for this. But of course, there is a limitation in terms of substrate used for this reaction, and we will discuss that in a moment. Okay. Let us look at the catalytic version of these reactions. Okay. First catalytic Poisson-Khon reaction. Poisson-Khon reaction. Now, the substrate, unsurprisingly it is an intramolecular substrate, okay, where you have alkyne and olefin, terminal alkyne and terminal olefin together. Now, the catalyst that was taken is 3 to 10%, that is the again the catalytic first catalytic version, and dicobalto octacarbonyl species, 10%, 10 mole percent of the ligand, that is ether version of it, and 3 atmosphere pressure of CO, 120 degrees C in DME solvent, 48 hours and so on, and the product as expected is the one oxidative after oxidative cyclization under Poisson-Khon condition. Now, this becomes very standard, and nearly 80% yield, greater than 80% yield can be obtained for these products. Now, that becomes the standard or the hallmark for this sort of reaction. We have seen nowadays whatever Poisson-Khon reaction we do see, usually the reaction conditions are quite similar to these. Okay. A variety of these substituted Poisson-Khon products, cyclopentanone, can be synthesized by utilizing this technique. The yields are usually on a higher side, 80 to 90s, 80s and 90s for this. Different substituent can also be tolerated under this condition. Well, let us look at more of an intermolecular version, where we will see, always we were so far discussing the substrate where alkyne and olefin are together within one. Now, we will get the intermolecular feeling for these reactions. Well, let me first give you the reference. This is a Jacques by Chang and Jiang 1994 1163159. This is the reference for this, and then we will now discuss the intermolecular version, where we will take norbornene type of substrate. So, it is a highly substituted one, and of course, it is also a strained one. Now, that alkene as a substrate and first intermolecular version was reported. Okay. Once again, with catalytic amount of cobalt, that is considered quite a way forward for this kind of reaction at that stage. Okay. Let us look at intermolecular catalytic Poisson-Khon reaction. Okay. So, you need strained olefin for intermolecular reaction. The simple olefin simply does not work. You need strained olefin, and you can react it with alkyne. Terminal alkyne, of course, is the best. Overall you get the product that one would expect for this sort of reaction, and that is the strained cyclopentanone type of moiety can be synthesized very easily. And the catalyst that is used for these reactions are the one where you have the cobalt in it along with cobalt-to-zinc cod moiety together. Now, this is reported by once again Chang and Jeong in JAX 1994, and this is a very good effective reaction. Not only this, you can take terminal alkyne, different alkyne can be reacted quite efficiently utilizing this technique. Let us look at some of the specific example by utilizing this norbornene or norbornadiene as an olefin counterpart along with an internal alkyne or terminal alkyne to give you the Poisson-Khon product, which was reported in mid 90s. Okay. Let us look at those examples. So, we will take norbornadiene as the first example, where phenylacetylene is utilized as the substrate to give you the final product, where once again the desired cyclopentanone ring is formed quite efficiently. This is nearly 90% yield, and if you are taking a propargyl alcohol, once again you can get the product, the desired product with this once again with norbornadiene, and this regiochemistry is quite efficient, and only one product is forming usually for these cases. And if you are taking an internal alkyne, that is also possible to react quite efficiently, and that gives the product once again quite efficiently under the condition. The cyclopentanone product, the desired cyclopentanone product are formed. As you see, phenyl is right next to the carbonyl, methyl is there. So, these are quite efficient. Of course, these intermolecular reaction condition, intermolecular Poisson-Khon reaction, and that is under the catalytic amount of the cobalt catalyst. Cobalt is used for these reactions. You can usually, the only limitation that we can see for these reactions is it has to be strained olefin such as norbornene or norbornadiene, as we have seen in these cases. Of course, under this reaction condition one can do the intramolecular reaction as well without any problem. The yields are even pretty good. 100% product formation can be obtained with this, of course. So, now as I was telling, not only it is possible to do the catalytic Poisson-Khon reaction, it is possible to do intermolecular catalytic Poisson-Khon reaction, it is also possible to do the asymmetric version of these reactions by utilizing a suitable ligand for the metal center. Now, instead of cobalt, initially people were using titanium as the titanosin compounds for this sort of reaction. Let us look at the asymmetric version of this Poisson-Kohn reaction, which could be quite interesting because there are desired target molecule where we need this stereocenter to be generated. So, asymmetric Poisson-Kohn reactions. Of course, these are again catalytic asymmetric Poisson-Kohn reactions. Well, we will take the intermolecular version, of course, at this point. Okay. So, that is rightly and nicely set. You take 5 to 20% of the titanosin complex and CO 14 psi, toluene and 12 hour 90 degree C, you get the stereocenter that could be generated right over here, and then cyclopentanone can be generated from this product quite efficiently. The catalyst that is used for these cases are quite interesting one, and nowadays it is a very familiar one and popular one as well. And this gives the product quite efficiently, and this product formation can be done under very mild condition, relatively mild condition, as you see 90 degree C is very efficient for this sort of product. So, this is EBTHI, that is how they abbreviate titanium dicarbonyl species. This is SS version of it, and this is giving the product quite efficiently as we mentioned, and we get the asymmetric center generated in a very high EE, something like greater than 90% EE for most of these cases. Okay. This is reported by Buchwald in JACS 1996 118-11688. Okay. And also there is a recent review in 2006 by Shibata in Advancing CAT in 2006, you may want to read. So, the yield for these sort of reactions are quite good, and enantiomer selectivity is usually greater than 90, that is efficient for this sort of reaction. And as you can see, by using these titanosin reagent, Buchwald and co-workers were able to get very efficient reaction, and the stereochemistry can be set quite nicely, and that could be a very useful method for natural product synthesis. So, we have once again see an intramolecular version of the Poisson-Kohn reaction, where alkyne and olefin are put together along with carbon monoxide, the 14 psi carbon monoxide at 90 degree C, which is a very good reaction condition to give you the good yield and good enantiomer selectivity for these reactions. Plenty of examples you can look at in that reference, or different substituents are also tolerated, different functional group were also tolerated under this reaction condition. Let us look at another example of asymmetric Poisson-Kohn reaction before we close this. Okay. So, we will be looking at Poisson-Kohn reaction in asymmetric version once again. So, catalytic asymmetric Poisson-Kohn reaction, in this case we will be looking at the example where you have an internal alkyne yet. We will come back to the mechanism of it, and 3% rhodium chloride, rhodium 1 CO2 was used along with BiNAP and silver OTF, 1 to 3 atmosphere pressure of carbon monoxide, THF 90 to 130 degree C is usually used. This is a using 3% rhodium catalyst. Now this can also give the so BiNAP is the one which is the chiral ligand in there, and you can get the desired product efficiently by utilizing this method. And in these cases yields are usually 80 to 90s, EEs could be little low 70s, but those are quite efficient without any problem. This can be done, and different variation as well as the substituents are tolerated under this reaction condition. Okay. So, we have seen two asymmetric reactions. One was with titanosin compound, another was with binaf rhodium compound, which is quite interesting, and you can get the you can get the reaction yield quite high. EE could be varying from 60 or 70s to 90s, but overall this is a reliable method to form the desired Poisson-Cohn product with an asymmetric center in them. Okay, in a moment we will look at the mechanism of that Buchwald's example where titanium catalyst is used. Okay. So, once again this is a very simple Poisson-Cohn type of reaction mechanism that we were discussing earlier. Let us look at that example where Poisson-Cohn reaction mechanism is discussed. So, the ligand that we were using is that EBTHI titanium dicarbonyl species. From here on, the substrate that is required is intramolecular this alkyne and olefin 1, and this substrate comes in, one of the carbon monoxide goes out, and overall you form a cyclopropene titanocyclopropene intermediate, and that gives the substrate interaction first. That alkyne interacts first with titanium, and then the olefin is right over there. Of course, you have EBTHI that ligand with it, and subsequently you get the product where titanium is in 5-membered metallocycle formation mode, and with the substituent. So, the alkyne oxidative cyclization between the alkyne and olefin is taking place right now, and that gives you the intermediate like a 2-fused 5-membered intermediate. From here on, carbon monoxide can be inserted into this titanium metallocycle intermediate, overall giving a 6-membered intermediate right now. Subsequently, reductive elimination can give you the product formation from these cases. So, the desired product, Poisson-Cohn product, can be formed with asymmetric center in it quite efficiently by utilizing this technique. So, what in this mechanism what we have seen so far, the titanium reagent is interacting with the alkyne first to form the cyclopropene type of intermediate, titanocyclopropene intermediate. Of course, the chiral ligand is attached with it with the titanium, and then this intermediate cyclopropene titano intermediate interacts with the olefin and cyclization occurs. So, it gives you the fused 5-membered intermediate where one of the 5-member is having the titanium in it, then carbon monoxide gets into that 5-membered metallocycle intermediate, and finally reductive elimination gives you the product, Poisson-Cohn product with asymmetric center induction in it. So, the cyclization path or cyclization step is determining the stereochemistry of the product that we see finally. Of course, during the reductive elimination, once regenerate the catalyst to go on for the next cycle. Well, we have seen the versatile Poisson-Cohn reaction, their application for various natural product synthesis. We have seen the stoichiometric version first, intramolecular stoichiometric version, then intermolecular reactions along with the catalytic version, catalytic intra and intermolecular version, and finally we have seen the asymmetric version of these Poisson-Cohn reaction. We have seen one example from Buchwald group, another we have seen with the rhodium. Along with this, and the mechanism also has been discussed briefly for this sort of reaction. Now, as you see, various other metal of course, it started with cobalt, then we have seen titanium and rhodium also have been used. So, now Poisson-Cohn reaction is widely applicable both in industry and academia, and it is the most reliable technique to synthesize cyclopentanone or its derived compound, and it can be reliably synthesized. As you see, even the enantioselectivity can be very high for these reactions. So, with this we would like to conclude today's class, and keep studying this oxidative cyclization reaction, and feel free to ask questions as you may have. Thank you.